Here is a single stationary vector suspended in space. Watch its numerical address. As the background grid shifts from a standard square to skewed to rotated, the vector's physical position never changes, but its coordinates rewrite themselves completely. To understand why a vector's data can mutate while the object remains identical, we rely on the rigorous definitions in Hoffman and Kunze's linear algebra. Grasping the exact mechanics of basis transformations and coordinate changes is a mandatory requirement for clearing advanced mathematics exams like the CSIR NET, the GATE exam, and IIT JAM. The coordinates you assign to a vector are entirely relative to your chosen point of view, but the underlying geometric capacity of the space, the dimension, remains constant. We anchor abstract vector spaces using what Hoffman and Kunze define as an ordered basis. This is a finite sequence of vectors that is linearly independent and spans the entire space. The word ordered is mathematically vital. Because an ordered basis is a sequence, every element occupies a specific fixed position. The first vector is strictly the first, and the second is strictly the second. This equation shows how an ordered basis works. A vector alpha is constructed through a unique linear combination of basis vectors. The specific scalars, x1 through xn, are the coordinates. Extract these exact scalars and stack them sequentially to construct the coordinate matrix. Consider this 2D Cartesian plane. Our standard ordered basis consists of the unit vectors along the x and y axes. The coordinates are simply the scalars that stretch those two standard basis vectors to reach the target point. Now rotate the coordinate system by an angle, theta. We establish a completely new ordered basis, derived from sine and cosine functions. The plotted vector remains frozen in space. It has not moved. But because our reference frame rotated, the scalar multipliers have completely updated. The vector's identity holds. Its coordinate representation shifts. This logic applies equally to abstract spaces, where visual graphing is impossible. In Hoffman and Kunze's example 20, they map a vector in a three-dimensional complex space. Translating a standard complex vector into a highly non-standard basis involving imaginary numbers requires calculating an inverse matrix to determine the precise new scalars. The spatial reality stays the same. The arithmetic adapts. We can expand this further. In linear algebra, a vector does not have to be a geometric arrow. A vector can be a function or a polynomial. In a space of polynomials up to degree 2, the standard basis sequence is 1, x, and x squared. Any polynomial in that space maps directly into a simple column matrix, using its coefficients as the unique coordinates. The basis acts as the structural template. The coordinates are simply the specific data points you plug into that template to isolate a single element. If you can pick any set of vectors to be a basis, what mathematically prevents a set from qualifying? First, the set must span the space. By scaling and adding the basis vectors together, you must be able to reach every single conceivable vector in that space. Second, the set must be linearly independent. There can be zero redundancy. No vector in the set can be built out of the others. Look at this plane formed by two independent vectors. If we add a third vector flat against that same plane, it provides no new directional reach. In R2, with vectors 1, 0, 0, 1, and 1, 1, that third vector is entirely redundant. It breaks down perfectly into the sum of the first two. This redundancy destroys the entire system. If vectors overlap in their reach, there are suddenly infinite ways to write the coordinates for a single point. A basis requires uniqueness, so a dependent set fails immediately. Hoffman and Kunze formalize this limit in Theorem 4. If a vector space is spanned by m vectors, any linearly independent set in that space must contain less than or equal to m vectors. This theorem mathematically caps the size of any independent set. You cannot cram 4 linearly independent vectors into a three-dimensional space. The math will not allow it. The direct corollary to Theorem 4 is that every possible basis for a specific finite-dimensional space will always contain the exact same number of vectors. This universal, unchanging integer is defined as the dimension of the space. The space of n tuples over a field has dimension n. The space of m by n matrices has dimension m times n. We can use Theorem 5 as a practical tool for constructing these spaces. It proves that any linearly independent subset can be systematically extended, vector by vector, until it forms a complete basis. Start with one non-zero vector to span a line. Add a second independent vector not on that line, and you span a plane. Add a third independent vector outside that plane, and you span a three-dimensional volume. You repeat this until you hit the dimension cap limit. You can invent an infinite variety of skewed coordinate systems to navigate a vector space, but the dimension remains the fixed number of vectors required to describe it, a property that survives any change in perspective. If the coordinates of a vector depend entirely on the basis, we need a systematic way to translate data from an old basis to a newly chosen one. We achieve this translation using an n by n transition matrix, labeled matrix P. This equation defines the relationship. The coordinate matrix of a vector in the old basis B equals matrix P multiplied by the coordinate matrix of that same vector in the new basis B prime. To construct matrix P, we look closely at its columns. The columns of P are simply the coordinates of the new basis vectors, mapped out and calculated relative to the old basis vectors. Because the new basis vectors are linearly independent, Theorem 7 guarantees that matrix P is always an invertible matrix. Its determinant will never be zero. To find our new coordinates, we algebraically rearrange the equation. We multiply the old coordinates by the inverse of matrix P. Input the old coordinates, apply the inverse matrix operation, and the new coordinates are reliably output on the other side. Matrix multiplication serves as the perfect geometric dictionary. It allows us to flawlessly translate numerical data across entirely different spatial reference frames. Let's now synthesize the architecture we've built. This diagram outlines our three pillars. The basis is the independent, spanning skeleton of the space. The dimension is the unchanging mathematical size of that skeleton, and the coordinates are the strictly relative addresses used to locate data within it. For those preparing for the CSIR NET, GATE, or IIT JAM exams, there is a specific mechanical trap in this material that routinely costs points. Notice the notation on this chart. When writing out coordinate matrices, Hoffman and Kunze strictly require the use of vertical column matrices. Never write your coordinates as horizontal rows. If you formulate your coordinates as row vectors, your inner dimensions will not align when you attempt to multiply by the transition matrix P. The calculation will fail immediately. Furthermore, be exact with your direction of translation. Matrix P is built by expressing the new basis in terms of the old system. Reversing that relationship will yield an entirely incorrect coordinate mapping. If this breakdown clarified linear algebra for you, like this video and subscribe to the channel for more rigorous deep dives into advanced mathematics. Keep practicing your proofs, and always return to the source text for ultimate clarity.